Quadratic equations can have complex solutions. We're going to take a look at this example here, which we could solve either using the completing the square method or the quadratic formula. Completing the square is always a good choice when your quadratic equation has a leading coefficient of 1, which this one does, and your middle coefficient is even. So this would be the fastest method to use to solve this equation. But the quadratic formula also works. So let's go ahead and do it both ways really quickly. By completing the square, what we do is we get our x terms together, and then we leave a little bit of a space, and we move that numeric term to the other side and give it a little bit of space too. I'm going to add a number to both sides of the equation. The way I get that number is I take the coefficient of x, I divide it by 2, and then square. And that's going to always give me a positive number to add here, which is why I didn't really pay attention to the sign in front of the 2. So 2 divided by 2 is 1. 1 squared is 1. And the magic of doing this is that my x squared minus 2x plus 1 on the left-hand side is a perfect square. It's equal to x minus 1 quantity squared. On the right side, I have negative 5 plus 1, which gets me negative 4. I now complete this using the square root method. X minus 1 is equal to plus or minus the square root of negative 4. Then all I have to do is rewrite the square root of negative 4 using imaginary numbers. We've already done that. This is the same thing as 2i, because 2 being the square root of 4 and I being the square root of negative 1. And then add 1 to both sides. Gets us x equals 1 plus or minus 2i. It's also possible to solve this by the quadratic formula. It's usually a few more steps to do that because you end up with a radical that needs to be simplified. So we have to take a perfect square factor out of the radical and then still get through the whole simplification process without making any mistakes. That's really why completing the square is a better method. But I'll go ahead and take the completing the square steps out, and we will do this using the quadratic formula next. So using the quadratic formula, we get x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So this becomes 2 plus or minus the square root of 4 minus 20 over 2, which is 2 plus or minus the square root of negative 16 over 2. Now the square root of negative 16 we want to focus on for a moment here. That's equal to the square root of 16 times I, so that's going to be 4i, and I can bring that back into the expression now. And again, we want to break this into two separate ratios before we start canceling anything to make sure that we don't accidentally cancel part of a sum of two added terms. So breaking this into two separate ratios, I can now see the 2's cancel, leaving a factor of 1, and a factor of 2 cancels in this second ratio, leaving a factor of 2 in the numerator. So that the whole thing is equal to 1 plus or minus 2i, same result that we got using completing the square, but just in a little bit more roundabout way. And now that we have established complex solutions of quadratic equations, we can take a look at this discriminant. Recall that the discriminant is the expression inside the square root of the quadratic formula, b squared minus 4ac. This is called the discriminant. And its sign tells us what type of solution we'll have and how many. If that discriminant is positive, we already established that we get two real solutions. If the discriminant is 0, we already established we get one real solution. And when the discriminant is negative, previously we had to simply say no real solutions. Now we can be a little bit more specific and say two non-real solutions. And by non-real, I mean complex with non-zero imaginary part. Sometimes we shorten this by just calling them imaginary solutions. But really, to call a number imaginary suggests that it's pure imaginary and does not have a real part. So it's a little bit more precise to call them non-real solutions. But if I ever just refer to them as imaginary solutions, what I mean is that they could have a non-zero imaginary part. So using this information, I can now look at a graph that represents a function. And we're asked to use the graph to predict the number of real zeros and the number of imaginary zeros. Remember that the real zeros are the same as the x-intercepts. So we can just glance at the graph and see how many x-intercepts it has. In this case, the x-axis is down here and the graph is entirely above it, so we can see that there are none. Which means that all of our zeros are imaginary. Just thinking back to the three cases in the discriminant, we could possibly have two real solutions, one real solution, or two imaginary solutions. Nothing else is a possibility, and this tells us that we must be in the case where we have two imaginary zeros. So we already know what kind of numbers our zeros are going to turn out to be. And again, imaginary or non-real is the way to describe this kind of zero. Now I'm going to find them symbolically using the formula. So the function we were told is x minus 4 quantity squared plus 20. And since we're trying to find zeros, we're going to just set it equal to 0 and solve this equation. Even though it is possible to multiply this out and apply the quadratic formula, it will be a lot more work to do that than it would be to just use the square root property on this equation. Our x appears only once. Remember that that's the only criterion. If it's a quadratic equation, the only criterion we have for it being a good candidate for the square root property is that the variable appear once in a squared expression. So I'm going to subtract 20 to the other side and just get x minus 4 quantity squared equals negative 20. And then I'm going to take the square root of both sides, which clears the square on the left. And I have to consider both the positive and negative square roots on the side with the number. And now, again, I want to think about simplifying the square root of negative 20. So the square root of negative 20, I'll first think of it as I times the square root of 20. The negative comes out as a factor of I. And then 20 has a perfect square factor of 4. Leaving a remainder of 5. So I'm going to rewrite the square root of negative 20 as 2i times the square root of 5. We therefore have x minus 4 equals plus or minus 2I times the square root of 5. And if I just add 4 to both sides, to get these in the form a plus bi, it's best to just put the real part first and the imaginary part last. So I'll write this over here where we have a little bit of space. X is equal to 4 plus or minus 2I times the square root of 5. If I need to enter those as comma-separated values, I would have to split apart the plus or minus. So over here in this lower corner, I'll write that as 4 minus 2I times the square root of 5, comma 4 plus 2I times the square root of 5. Doesn't matter what order we write these in. They really don't have any natural ordering anyway because they are not real numbers. We couldn't plot these on a number line.